So I want to look at an example that if you've taken real analysis yet, you've seen this, and if you haven't, then that's okay. You'll have a sneak preview. So we're going to look at what's called the Dirichlet function, and so there's different ways to define it. We're going to actually break from our book. Our book puts a -1 here where I've put a 0. It doesn't matter. It's a function from the reals to the reals, and when you plug in a real number, f sends it to 1 if what you plug in is rational, and f sends it to 0 otherwise. And so just to be very, very clear here, f of 1/2 is the same as f of -10 to the 10 is the same as f of 2. All those get sent to 1 because they're all rational, but f of pi is the same as f of -√2 is the same as f of e, which is 0. So that's how the function works. And so we want to ask several questions. So is f continuous when its domain, which is R, by the way, and its codomain are endowed with the standard topology? So we're going to stick the standard topology here, and we're going to ask ourselves, is this function continuous when you have the standard topology? And so let's think about it. So the standard topology, you can think of the definition, but really the key that we learned later on was that we know that open set under the standard topology, these are just unions of open intervals. So you're an open set if and only if we can write you as a union of open intervals of finite length. And we covered that earlier in Chapter 2. We saw that the set of open intervals form a base for the standard topology, which is really nice to know. All right, so let's just play around a little bit rather than me tell you the answer right away. Let's try to play together a little bit. Maybe you should pause the video and have a guess, and then come back in a minute and we'll do some examples. So let's think about the preimage of the interval 0 to 1. This is the interval of real numbers 0 to 1, not including 0. So 0 is not in there, 1's not in there, but everything in between is. And if you think about it, gosh, this is the set of x in the reals such that f of x lies in this interval. And you should realize, well, wait, hold on. F sends things to either 0 or 1, and neither 0 or 1 are in that interval, so this is just the empty set. And that's actually good news. The empty set is open. So here is an open set whose preimage is open. That's good. Okay, we have a long way to go. If we're going to check all of these, we're going to be here forever, but let's play around a little bit more. What if I took the preimage of, how about we do the set -1 to 2? And so this is, again, the set of x in R such that f of x, which, by the way, is either 0 or 1, and that needs to lie in this interval -1 to 2. Well, please notice that 0 is in there and 1 is in there. And so that means everything is in there. So the preimage of this set is actually all of R itself, which again is open. So far we've checked 2 out of infinitely many things, and we've had success, but really that's not good. Let's look at another example. So hopefully you can kind of see where the problem is going to happen. Let's look at the preimage of, let's say, the set, I don't know, let's go 0 to 3. So I'm going to look at the open interval 0 to 3. Notice that 0 is itself is not in there, but 1 is in there. So 1 is certainly, hold on, I'm not writing this very clearly. I'm not talking about the preimage. This set right here does not contain 0, but it does contain 1. And so when you think about it, you realize, okay, this is the same as saying all the stuff that f sends to 1, which is just the rational. So the preimage of that interval is just the rationals, right? Everything else goes to 0, which is not in that set. So all of a sudden we realize, wait a minute, the rationals, we've actually studied this together. That's not an open set. under the standard topology. So at this point, we know that, I'm kind of out of room, but we know that this is not, this function is not continuous. So let's squeeze that in. Maybe we'll change colors so that it kind of pops somehow. How about we do a bright pink? So we can say f is not continuous. Okay, a little tight there. So what happens if we change the topology? I thought it would be nice to play. So we're still having the same Dirichlet function f from the reals to the reals, but instead of equipping both the domain and the codomain with the standard topology, let's ask ourselves what happens if we change it. So let's think about it where we have f is the indiscrete topology. Indiscrete topology, right? That's the only open sets are the empty set and all the reals. And R is any other topology that you want on R. And I claim that f is R to f continuous. And so the way that I'm thinking about it now, just to be very clear here, when I say R to f continuous, I'm telling you where the topologies go. So I'm saying f goes from R to R, and so R to f continuous means I'm putting the random topology R on the domain, and then the indiscrete topology f on the codomain. Let's see if we can prove that this is the case for any topology R that you want, as long as you have the indiscrete in the codomain. Well, let's think about it together. So we need to check the preimage of all the open sets, but there's only two, right? So here, f is just the empty set and R itself, and it's pretty easy to see that the preimage of the empty set, that's not what I meant to write. The preimage of the empty set is the empty set, and the preimage of R is R. And both of these, I don't know a lot about my topology curly R, but I know that it always contains the reals, the whole set, the reals, and the empty set. So we can say these are both in my curly topology R, and so thus we can say f is curly R to curly f continuous. So that's nice. One more example, same setup, same function f, going to change the topology slightly. So now we're going to have, again, f is going from the reals to the reals, but now I want to put the discrete topology on the domain, and then I want to put a random topology on the codomain. And so I claim in this case that f is curly f to curly R continuous. Let's prove it. So how do you do that? So you need to choose an open set U in R. By the way, we don't know a lot about R. All we know is it's a random topology. And so then I want you to realize that the preimage of U is certainly it's certainly a subset of the reals, right, by definition. And wait a minute, what topology do we have? We have the discrete topology. So since the preimage of U is a subset of the reals, then automatically the preimage of U is trivially in F, because F is the set of all possible subsets. And so we're done. So we can say thus F is curly F to curly R continuous. So these examples are just to kind of show you how it works, and we'll try to come back at some point and look at our classic notion of continuity as well. All right, well, in the next video I want to introduce arguably the most important definition in this course. So I will see you in just a minute.